I'm Jack Brennan, a researcher at the University of Glasgow.
And I'm Martin Weides, Professor of Quantum Technologies and Director of the James Watt Nanofabrication Center.
So, we're here to talk about the recent Nobel Prize win in physics. So, do you want to give a brief overview of what was awarded and why?
So the 2025 Nobel Prize in Physics was awarded to John Clark, Michel Devery, and John Martinez. They showed the strange world of quantum mechanics, things like quantum tunneling and superposition and energy quantization isn't limited to atoms, so to tiny particles. It can also happen in much larger circuits, much larger structures that you can literally see with your naked eye, or you can hold the chip in your hand. And by using superconducting circuits, where many charged particles are collectively moved together as one macroscopic particle, they proved that these circuits can tunnel through energy barriers and also absorb or emit energy in fixed packets, just like atoms do, atoms jumping between energy levels.
So, before we get to why the discovery is important, what is your connection to the Nobel Prize winners?
Well, I mean, we're working in the same field, of course. So I joined Glasgow in 2018, but I before had postdoc positions. One of them was actually with John Martinez at Santa Barbara, UC Santa Barbara, California. And before that, even I worked in superconducting quantum circuits, and their work, which goes back to the 80s, has been really opening the field, widening the field for many, many years. So I personally work with them, but also our work today is really based on their achievements.
And you said that your research, our research actually here in Glasgow, is based on the work done in the 80s. So what comes next? What's the next big breakthrough? What are you working on now?
Well, so in our work, we're not building quantum computers. That's done by large corporations. With many, many teams. So in our academic work, we are looking at the fundamentals of quantum computers. So we look into single qubits or few qubit systems, and we are interested in solving the scalability problem. So to build a quantum computer, you would need many, many qubits. Today's quantum computers have about 100 to 1,000, but to be really truly useful, it would need 1 million or more. And there are some severe engineering challenges to go from 100 to 1 million. One of them being just the qubit itself. So in our work, we're looking into different types of qubits which can operate at high frequencies, at high temperatures, and are also smaller in size, all of which will lead to better scalability to the required numbers of qubits to make it really useful.
Mm-hmm. And why is this award important for the quantum sector specifically? Why is it important that quantum computing or quantum circuits won a Nobel Prize?
Well, I mean, the award itself is for fundamental science. So it's really demonstrating that these macroscopic circuits behave as a single particle of quantum. But nowadays, I mean, 40 years later, there's a large industry working on quantum computing because it has such great potential, and it can also provide an alternative to the energy-intense classical compute which you see in data centers, where we have sometimes even have nuclear reactors packed next to the hyperscale data center. Quantum computing was shown to be much more energy efficient. So how does it relate to quantum technology here in Scotland, here today? Now, Scotland has a large photonic industry, and not so much superconducting. That has changed with my arrival, and over the last couple of years with more research teams here in Glasgow working on this and related fields. But there's a direct connection to the photonic industry in Scotland. Now the quantum computer, the future quantum computer, will not be just based on superconducting circuits or semiconducting circuits alone. It will also need photonics, and it will actually need a mix of all these different technologies. And today we see a large activity on integrating hybrid quantum technologies to drive scalability, like connecting superconducting circuits sitting at deep cryogenic temperatures with photonic interfaces, so that the quantum computers can be actually interconnected, can be linked up through optical fibers. And that would mean we go from a microwave state, at deep cryogenic temperatures in a cryostat, to an optical state through an optical fiber to another quantum computer, maybe in the next city. And the photonic components are really key.
Well, thank you very much for your time today. It was excellent, very interesting.
Thank you very much. Thanks all.